seems to me that the history of physics has been a history of different descriptions of the way the world and the universe works. And not just different descriptions, but more useful descriptions, possibly more accurate descriptions, but the way I look at it, more encompassing descriptions. You know, the kind of physics that, or the kind of physical descriptions that Aristotle produced. They're absolutely fine as long as they're only applied to, you know, the surface of a planet of about our size, really, and operating at the kind of speeds that human beings operate at on that planet. I mean, if it seems bizarre, you had this idea of, I think it was Aristotle who had this idea of entelechy, which is the desire of an object to go to its natural resting place. So stones fall to the ground when you drop them because they have a kind of desire, I don't think he used the word desire, but that kind of a tendency to go to the natural place where stones are found, which is on the ground. And fire and smoke rises because the natural place for fire and smoke is in the Empyrean. It's that kind of an idea. I'm not quite sure about birds, but anyway. And of course it's bollocks, isn't it, really? But in terms of a description of what happens on the planet that we live on, it's pretty accurate, you know, and you can use it to base predictions on. You know, if you pick up a stone in a different part of the country or a different part of the world, and you have this idea of entelechy that all stones want to get to the ground, you can make basic predictions on that. They're rough and ready and heuristics rather than laws, but you can do that. When Newton described physics, it's more encompassing. As I say, it's more accurate as well. You can make much more accurate predictions about the specific motion of various things. But it's also more encompassing, isn't it? You know, it doesn't just apply to the surface of a planet. It applies to the planets themselves, and it applies to, you know, any kind of heavenly body or anything really. And of course, it's framed in mathematical language, or begins to be able to be framed in mathematical language, I suppose I should say. It doesn't contradict what Aristotle says in a sense, how the predictions come out the same. It's just that Aristotle's predictions are very, very, very context dependent, whereas Newton's predictions are much more, it's the same, more encompassing. Then of course when you get to Einstein's physics, or his descriptions, it applies to a much wider set of phenomena. So it doesn't just apply to large lumps of stuff moving at a stately pace in the heavens or on Earth. It applies to tiny things moving really, really fast across vast areas of space. And that, you know, relativity effects kick in. So he's able to describe a wider set of parameters. And similarly with quantum theory later on, it's another description, arguably more accurate, you could say that, but certainly more encompassing. Those equations, you're able to describe phenomena not only on this scale on planet Earth, not only in the Newtonian heavens, not only at speeds approaching the speed of light, but also at you know, tiny scales and all that really. So these are just a succession of descriptions which are not exactly different. I mean, they are different in a way, but they're not exactly different. What's more important for them, I think, is that they're more encompassing. Come on, pups, this way. Which for me has a relationship to that Thomas Kuhn idea of paradigm shifts. Because the idea of a paradigm shift, which is from his book The Structure of Scientific Revolutions, the idea of that is that, you know, occasionally you get these fairly momentous revolutionary overturnings within the scientific descriptions of the world, in which one set of understandings of the way the world works is completely overturned by a new generation of scientists working with a different paradigm, with a different model of how the world works. And his usual example is the Copernican revolution, you know, when Ptolemy's model of the sun-centered cosmos was replaced by, you know, Copernicus's model of the, I beg your pardon, the Earth-centered one was replaced by the sun-centered one. But in a way, just putting that example to the side for now, in a way I think that that progression of different descriptions of the physical universe, you know, through, as I said, Aristotle, Newton, Einstein, Niels Bohr, Schrödinger and those chaps, it's there's no overturning that takes place there. You know, Newton doesn't disprove Aristotle, it just says Aristotle's descriptions are about this much of the physical world. a physical world which is very closely rooted in human experience, actually. And similarly, Einstein doesn't disprove Newton in any meaningful sense, or doesn't, for the most part, doesn't disprove Newton. It just extends those findings and explains a greater set of phenomena. And again, with Niels Bohr and all that quantum mechanical stuff, Einstein doesn't go out the window with that completely, and neither does Newton, neither does Aristotle. It just recognises that those other descriptions refer to quite limited subsets of the entire phenomena that's available in the universe, really. And there'll probably be others. There'll probably be another description of the universe coming up at some point, which renders quantum mechanics as evidently a description of only a small portion of what's actually out there. Well, so in a way they're not. So what I'm saying there is the idea of the paradigm shift coming along, and the whole thing and everything that came before being rendered obsolete, I think is a bit wrong, really. I think it's more that it's rendered partial, or shown to be a particular limited case or limited set of circumstances in which that description holds true. You could even say that about flat Earth theory, actually. I was thinking about this a while back. Flat Earth theory, of course, is complete bollocks. But if you're a carpet layer, or if you're a person who designs the foundations for houses, you're basically using flat Earth theory. You assume the Earth is flat. And for all intents and purposes, within the very limited context of your practice, laying a carpet, measuring the foundations of a house, town planning even, it works in the description of the Earth as a flat thing. Works absolutely fine. It's only when you need to do space travel, or global mapping, or sailing from one continent to another, that kind of thing, that you really need to understand the Earth is not flat, but as curved. Yeah, I suppose that's even true of the Copernican revolution, isn't it? And of course it doesn't make sense to think of the Earth as flat, I beg your pardon, to think of the Earth as the centre of the solar system, centre of the cosmos, except on a routine level we do. As a rule of thumb, as a description of what it's like to live on planet Earth, it works absolutely fine. It does feel like the Earth is stationary. It does feel like the sun rises in the morning and sets in the evening. As long as you limit the description to a very prescribed set of circumstances, the Earth-centered cosmos is absolutely fine. And similarly, actually, the Copernican model of the sun-centered model isn't exactly true either. When he's saying that, he's just putting his thumb on the sun and calling that the center. But we all know that the sun is actually flying through the galaxy at millions of miles an hour, vaguely in the direction of Alpha Centauri or whatever. You know what I mean? With the planets kind of whipping around like the reins of a horse. So that's only partial, I think. Yeah. So this idea of a progression of more encompassing descriptions, I think, gives the lie to the idea of paradigm shifts as truly revolutions. They're more like extensions, expansions.